Hello everyone. In this video, we are following chapter F4.6, fitting functions to time series from the book Cloud-Based Remote Sensing with Google Earth Engine. We learned to use linear modeling and retrending the time series in this chapter. We also learned to determine the trend and seasonality on a 4-pixel basis from the multi-temporal data. There is also a previous video on the channel that explores this concept, but as part of our book series, we are revisiting it to reinforce our understanding. We will keep the code brief and focus on recapturing the main ideas. So why do we need this? We see the regular increase and decrease in natural phenomena. For instance, during the season, NDV captures the seasonality with increase and decrease of its value as there is the changes in the presence of vegetation. Earth Engine helps to identify the linear trends in the study area where linear regressions can reveal linear trends over the years. Also, the harmonic terms, when we fit them, we get the sine wave-like curve. This helps us in defining the vegetation changes over the time and even track the changes year to year and observe the deviations from the expected patterns. Observing these deviations from the expected patterns can identify and observe the events such as deforestation and forest degradation. During our analysis from the image collection, while we use the different types of filters and maybe the clouds and from our own choices, this changes the number of the observations in those dates. This changes the length of time series, and even sometimes we get the missing data. So for that, we have two important concepts for the multi-temporal data. The first one is the per pixel or fitting. So here a function is fitted to the series of values in the form of equation that is y equal to mx plus bc. We estimate m and b from the set of x and y values. And in the time series, x is the time and y is the observation and the time. Interestingly, Earth Engine also estimates values across the large area. It fits the function in every pixel of the study area. Each pixel will have their own m and b values determined by the number of observations in that pixel. And also through the observed values and the dates for which they were observed. The second one is the higher dimension band values, that is array images. So there can be potential information present within a single pixel, and this information can be presented in a higher order Earth Engine structure called the array images. So it is possible for a single pixel in a single band of a single image to contain more than one value. In the array image, a single pixel might contain a one-dimensional vector of numbers with slope and intercept values resulted from a linear regression. In simpler terms, we are considering the images as arrays, and we are trying to use the functions from matrix algebra. Representatively, scalar pixel is given here as the t sub t and that time t, and the pixel vector as p. P hat here is the estimated value at the time t. So the time series is the collection of the pixel values sorted in the chronicle order. The t sub 0 will be the smallest time or the beginning of the time, and t sub n will be the time in lateral period. So let's try to briefly visit the codes. So here we have the USCS Landsat 8 Level 2 Collection 2 and Tier 1 image collection, and we are applying the cloud masking function. We add variables of interest to the collection as bands. So the NDVI the time variable and the constant variable with value 1 has been added to this image collection. We visualize the NDVI chart and the point of interest over time. We can also add the linear trend in the chart by the parameters in the dot set options here, trend lines for the image series chart, and we get these two different charts here. Time series dataset with trends may also contain seasonality. They should be removed before modeling. When they are not removed, they result in varying mean and a varying variance over time. So they can make the time series non-stationary. Stationary means where there is a stable mean and where there is stable variance. So in the linear model here, we have this ET. So this is the random error. And if we try to understand this model here, this is the linear model, and here P sub t represents the value of the dependent variable, and this P sub 0 means the intercept term. So this is the value when the t is equal to 0, and this is the starting value or baseline level of the dependent variable. We also have this beta sub 1t, and this is the slope coefficient. So it indicates the rate of change of the dependent variable with respect to time t. So if beta 1 is positive, P sub t will increase, and if beta 1 is negative, P sub t decreases as t increases. And this t is itself the independent variable that represents the time, and as time progresses, t takes on values such as 1, 2, 3, and so on. Then we have this E sub t, and this represents the error term or residual at the time t, and it accounts for the variability in P sub t that is not explained by the linear relationship with t. So it is initially assumed to be 0 or the random variable with the mean of 0. And there can also be many approaches similar to this, such as differencing and averaging and others. So removing unwanted and uninteresting trends for the given problem will help in understanding the complex pattern in the time series. We can remove the linear trend that is evident in the data using Orff Engine's built-in tool for regression modeling. So our goal is basically to discover the values of beta. So here we have the simple code to remove the simple code to feed the trend model to these Lancet-based anti-series using the ordinary least squares using this linear regression reducer. And this retrains the original NDVI time series and plot the time series chart with the trend lines parameter. Then we have the section 4, and to understand this, we have to understand this equation. So the time series can also be represented through harmonic trends, where a value goes up and down, in a predictable wave pattern. So harmonic changes in greenness of vegetation can occur across different seasons. So in the harmonic model, we have the A as the amplitude, and then we have this double-looking symbol as the frequency, and this symbol as the phase, and this E sub t as the random error. So to read this, we simply read this as P sub t equals to beta 0 plus beta sub 1t plus a cosine of 2 pi omega t minus phi plus E sub t. So this represents this PT, E sub t represents the value of the dependent variable at time t. and this beta 1 is the intercept term. So when the t equal to 0, it basically represents the baseline value of the dependent variable, and then we have the beta 1 t, and this is the slope coefficient, and it indicates the linear trend over the time. So if beta 1 is positive, p sub t will increase over time. If negative, p sub t will decrease over time. And this ACOS, this whole represents the periodic component of the model. So A is the amplitude of the periodic component, indicating the magnitude of the oscillations. And this omega or double looking symbol is the frequency of the oscillations. So that represents how many cycles occur per unit of time. And this phi is the phase shift, which indicates where its cycle, when in the cycle the oscillation starts. And this E sub t is the error term, which accounts for the random variations in P sub t. So we are trying to fit that equation in this, and this has also been written in another way. So basically, this is the same thing. The first equation is a little modified for the second equation, and this is this equation is being basically trying to fit that equation here. So we fit the model to an annual time series where this double looking sine or omega is equal to 1. That means 1 cycle per year. And we use the ordinary least squares regression. And we get something like this, sine wave-like graph, or the sine wave-like fitted trend line. So basically the curve is sine wave-like in sine wave-like form. Then we have the section 4 here, and in this we are fitting the model to add the harmonic variables, and we can also compute and map the phase and amplitude of the estimated harmonic model for each pixel. And this phase and amplitude gives us the ASLA information to facilitate remote sensing applications such as agricultural mapping and land use and land monitoring. So agricultural crops with different phenological cycles can be distinguished with this phase and amplitude information. Spectral information are not always helpful in this case, so we need this type of information. So we also compute phase and amplitude from the coefficients in this code and add this to the map. So this is the phase hue and amplitude image. So here phase, amplitude, and mean NDV are displayed in terms of hue. This in terms of hue, that means color, and saturation, that is the difference from white, and value, that means difference from black. So the darker pixel are the areas with low NDVI. So water bodies will appear as black as the NDVI values are 0 or negative, and the different colors are distinct phase values, and the saturation of the color refers to the amplitude. So whiter color means amplitude close to 0. So that may be the forested areas, and the more vivid the colors, amplitudes will be higher over there. So example, the croplands. This is the section 5 here. So in this section, it says that we can visualize the data in different ways. So rich data itself on the curve can be visualized in multiple ways. So the images is somewhere focused on the California and displays how sine and cosine coefficient values are transformed and integrated with the with mean and deviate information. So the visualization includes sine and cosine coefficients represented in red and blue. So this first image that is being displayed is that one. So here the sine and cosine coefficients are represented in red and blue, and it overlays the slope of the linear train that is calculated earlier, and that is in green. So we are visualizing different information that we have received. And here we have the section 6, when the agricultural field is double cropped. So modeling multiple growth cycles within a single year can be achieved by incorporating additional harmonic terms. So this code here is demonstrating how we implement these modifications. We adjust the values of the harmonics variable that so we are basically adjusting the values of the harmonics variable that alters the complexity of the harmonic curve by adding or removing harmonic waves, thus modifying how they overlap. So fitting higher order functions can enhance or change the model smoothness of fit to the data. So all the mini coefficients may become close to zero with higher number of harmonic terms. So this example demonstrates the fit using 1, 2, and 3 harmonic curves. So basically, let's understand in this way that harmonics are how many curves are there within the year. So that is the main thing. And finally, we have been assigned 2 NDVI harmonic modes for location near Brazil. So the model represents the period before a disturbance event, and other represents the period after the event. And we're getting some kind of the chart here where we are fitting the harmonic model in the NDVI. So basically, to conclude, the concept of fitting functions in the time series are very useful in identifying the trends, and this will be useful in upcoming chapters. So most important tools for monitoring environmental changes, such as continuous change detection and classification, and continuous degradation deletion, use these methods, and not only they help us in preserving our environment in applications regards, but they are crucial for understanding the changes in the land surface. So I tried to explain some of the things, but these are still kind of, I think, complex in its own ways. Please comment for any type of discussion. I would say thank you for watching.